So some of the things I'm going to talk about are going to touch on some of the topics that we've really already talked about to some extent. Again, this is more of a discussion type of format. And in some cases, some of these will be covered more in depth in either previous talks or in later talks. And so for the overview of topics, I wanted to talk a little bit more about the build strategies and how the images have to be created and packaged together. This is kind of a complex thing when you're dealing with secure and non-secure images. We're going to talk a little bit briefly on the bootloader support, and the device tree support bullet on here is really a kind of I'll do a little bit of a summation of the session that we had yesterday concerning this. And I'd like to say for the bootloader support, David here is going to have a nice presentation. Is it tomorrow or Thursday? Thursday about the MCU boot and things that need to be added to really support the multiple image support. So, build strategies. So, how many of you have had experience building TFM and integrating it with Zephyr? So you've done it, non-ARM people. Yeah, so 2 or 3 people. So, how did you find that experience?
Well, I didn't do it with Zephyr. I did it with our own kernel. But yeah, it's interesting.
Okay. So you can go out and you can actually check out the TFM repository today. You can do a build, and it produces some images that you can use. You can do the same thing with Zephyr. The issue is that when you start trying to mix together the secure and non-secure, you have to take a couple of things into consideration. I mentioned this earlier. You have to deal with the fact that your address space has been partitioned. You have to deal with the fact that the peripherals have been partitioned as well. So when you go and you link, let's say Zephyr or another RTOS, you have to understand that even though you may have an SRAM or a flash area of some size, you actually only have access to a portion of it, and it's also offset somewhere into that. So when you create your linking, you have to do the right thing. That doesn't even get you to the point of creating the final image. So now you've got, let's say you build TFM and you build Zephyr, so now you have 2 binaries. Well, how do you package these things together? Well, one of them has to be put starting in an image format at one point, and then the other has to be tacked on. Today there's a script that we use that kind of, it's usable, but it's not a great solution. Really what we would like to have happen is we would like to have one place where you say, okay, go build TFM, go build Zephyr, now package the thing, because it will know where the locations of all the output objects are. And then we would rather like to have one place where it understands how to stitch everything together. Today you have to do it manually. So a combined solution, like I said, working in Zephyr, my view of it is that I would rather have a Zephyr target where I say, go build TFM, and it goes, and since TFM uses CMake and we use CMake, it's just, it jumps to a directory, does a make, and it knows where the images are, okay? And then you do a build with Zephyr, and then you do a build with, I don't know, like make final image or something, well, yeah, some target. And then it would actually stitch it together and do the proper thing. Now that doesn't save you from misconfiguration of your security addresses and all that stuff, but it does at least get you an image that was put together properly. Out of curiosity, I mean, from a TFM perspective, what have you guys thought about how these things are packaged? Oh, you have a mic.
This is going to be a evolving topic. For now, the problem of building the non-secure side image and its handling those quirks, we have not given a lot of thought about that. Currently, the current way of thinking is that you build your non-secure image separately and the secure side separately. there is a script that combines the secure side boundary and non-secure side boundary and signs it together. So, and you can pass on the boundaries. It already knows where is the secure side boundary. You just need to provide the non-secure side boundary, and it knows how to combine it all together. So that's where we are today. I think feedback would be very much appreciated about what direction it should take. Yeah, so that's what it is today.
I guess the one thing I want to point out is also when there's one thing that we want to do when doing development. Usually we want to load all of the images in. When you're building a final product, it's usually very different. Generally, the images will be updated independently, that kind of thing. So I don't know how to take that into play. I mean, from our perspective, of course, we want what's most convenient where we can type make at the top. But we may need that case. Now, it may just be that you build both images and then don't use the one if you're not updating it for your update process.
Just a suggestion on this guy here on the spot. Trusted Firmware for A has a tool already called FIP, which does exactly that. You can package the different stage bootloaders, the secure OS, and add certificates, and it just generates a binary blob of whatever you say. So you give it on the command line, this image, this certificate, this image, this certificate. And I think right now it's very TFA specific, but there's no reason it needs to be TFA specific, right?
And there's a tool
It's just
like
a directory and a list of certs and blobs that it aggregates together.
Okay, yeah, we need to look into that.
MCU Boot has pretty much the same kind of tool that almost does everything we need, just not the second image. So maybe the solution is to enhance that tool or something like that.
Yeah. Thank you.
There might be more differences than you think.
100
kilobytes of RAM versus 3 gigabytes is a lot different.
No, I get that, but I mean, I'm just saying that if the tool is just stitching images together, so it just seems like, and it's taking certs and all that kind of stuff, so it seems like there's some benefit to just leverage a common tool across all of this, if possible.
We don't use certs.
Okay.
Yeah, I agree. Please contribute. There's another aspect to this. There's a supply chain issue when you're talking about the multi-vendor scenarios, where the secure side software could be developed by a secure software vendor, and then when you are talking about multi-vendor scenarios, there is a security aspect of the firmware as well, where you don't want the secure side image to be tamperable by the people lower in that supply chain. So there's that aspect, and today it is just thought process, but we are very far from getting to a stage where we can secure the supply chain part of it. But this is where I think the community can help and propose ideas and basically comment, ask questions on the Trusted Firmware.org project, submit RFCs, submit proposals, and if there is a contribution coming in, I don't think we'll ever, as long as it makes sense, of course, and any contribution will be taken on board. So today, I mean, we are focusing on providing a good programming model in the TFM because of the limited available capacity in the team. So the focus is not too much on sorting out the nicer to have things. So for me today, if I look at today's priorities, having a very clear separation of or having a very abstracted way of combining images is something nice to have, as long as we are providing a way of doing things, right? And once we have solved the initial problem of having a full programming model for the TFM, then we can come back and solve these problems. But if there is a contribution, it's always going to help.
Okay. And that kind of leads into bootloader support, because when you start talking about multiple images and updating specific pieces like you're saying, I mean, you may have multiple signed pieces. Some are provided by one group of people and then the others by the OEMs. So, and you want to be able to maybe update these independently of each other. And that goes to David's comment about, well, you know, how do you deal with these things? Do you deal with it all in one piece, or do you deal with it in one at a time?
The general conclusion we've come to on that is that you have to handle all of those, that there will be a scenario that wants each of the things you can think of.
Yeah. So with respect to the bootloader, today TFM uses a snapshot of MCU boot. I don't know what version it was, but with some changes, I think, on top, maybe. It's not, yeah, roughly 9 months old. We do need some additional things added to the MCU boot. And I think the real answer to all this is instead of forking it, we really need to be using the tip of MCU boot and adding what we need to MCU boot and carrying it forward, and then consuming it back into the project. I think that makes more sense. And David's going to have a presentation on Thursday about a lot of these things. So please do go to that, because it will be a very much deeper discussion about the bootloader. No. So one of the interesting things we did run across when we were messing around with the Musca is the fact that on that chip, it doesn't have onboard flash. It has an external flash, which is super slow. So when we do booting, we actually want to copy it to a faster location so we can actually execute. You know, it doesn't take 70 cycles per instruction. So we put that on the end. I mean, there may be people that want that type of thing, but there are definitely other features that we need to add.
Is bootloader running in secure world or not secure world?
What's that?
Is the bootloader running in secure world or not secure world?
Secure.
Secure world.
It has to.
Have to. Okay.
And ideally, you don't ever want to update that piece. You want it to be something that never changes. So any of the other images, perhaps you can upgrade, but not that. So
that means the MCU, after MCU reset, all the secure trust zone secure word will be enabled, right? The hardware secure feature, the trust zone, is enabled after hardware reset.
Yeah.
So we not switch to secure word in the bootloader, the boot code.
Well, it starts secure.
Start from secure.
Yeah.
Okay.
You actually demote at some point when you jump to the non-secure image.
Okay.
So. So any other questions on the bootloader before I touch a little bit on the discussions that we've had on the DT? Yeah. The question was, are we following the suit discussions? And the answer is yes. Yeah, David will update on that, but he's been participating in those meetings. Suit is the IETF group that discusses bootloader support, signing of images, and all that stuff.
Software update for IoT.
Yeah. It's a much better name than the previous one. What was it, FUD? Yeah. Yeah.
Could I just ask another question on the bootloader?
Sure.
The MCU boot, you said that's not updatable like all the other firmware. I guess that's on the assumption that that is the root of trust in the system. Is there a consideration of moving to a ROM-based boot flow in IoT devices? Or?
I don't know. I'll let David answer.
I mean, yes, it kind of has to be for it to really be a root of trust. You can fake it with some of these things where you flash.
Oh, you're expecting the full MCU boot to be in a ROM, not some kind of.
I mean, what ends up happening is you have a root of trust you need, and it needs certain capabilities, and that's basically what that's all that MCU boot has in it, is the minimum things that you need for a root of trust bootloader. So you could write another one, but it would have to do everything that MCU boot does. So
Well, you know, again, I'm looking at this from a
Yeah.
TFA angle, but you know, there could be a super minimal ROM which just
What do you consider
authenticates the next stage.
super
but
minimal? I mean, these things play.
It still has to authenticate the next stage, but it only has to authenticate one thing. If you're talking about
Right.
authenticating a chain of trust with multiple images, then that complexity could then be in a second stage.
Yeah, you could do another stage there, but you end up with a 16K bootloader that loads a 20K bootloader.
Yeah, you're
So-
right. If it's that kind of size, then it's not worth it.
Yeah, on a device that it doesn't have that much, so.
Is part of your concern thinking that these memories are off-chip and accessible, or just, is there?
Shall I just repeat your question?
I guess I'm trying to understand, you know, because there are some vendors that have done this where there are ROM-based secure loaders, and you know that they provide before, you know, with keys and so forth in hardware. So, but in these systems, and I just don't know where. I'm imagining a lot of the Cortex A level systems, your memories, ROMs, all that, or not ROMs, but you know, the flashes, things are off chip, so they're accessible. Where on these systems, typically, and the vast majority of them, they're in the SoC, so they're not typically. You don't have that security problem potentially of someone having physical access to scan out, or is that?
I'm not worried about the security problem. On TFA, the early firmware, all the secure firmware is running on chip anyway, usually. It depends on the design. I'm more thinking from a robustness point of view,
Okay.
keeping the ROM as small and simple as possible so it's not broken hardware.
So your absolute root of trust cannot have the same storage properties as the updatable root of trust, because the whole point behind updatable root of trust and whole idea behind image authentication is that you're trusting the previous stage and you're believing that the first stage bootloader cannot be tampered with. So if the tampering properties of the storage of the first bootloader, the root of trust, is same as the updatable firmware, then the point of doing the image check is kind of lost there, because you can as well modify the bootloader which is doing the runtime image verification, and then you own the whole stack. So there is a need to have a non-mutable root of trust, which will do the initial, which can do, and by the fact of being non-mutable, that bit need to be more trusted, not more trusted, but that need to be the absolute root of trust. Having said that, if BL2, the MCU boot is going to be treated as the absolute root of trust, it cannot sit at the same flash hierarchy as the runtime firmware.
Yeah. Any other? Okay. So I'm sure some of you attended the device tree support thing that we had yesterday, but this is kind of going to be a little distillation of the discussion that we had, but basically we currently already leverage DTS in Zephyr. We use that to describe mostly just the hardware and maybe some Zephyr specific things with the console, you know, some of the chosen stuff. But we've also had to kind of adapt that to deal with the secure and non-secure views of the system. Basically, we have systems where you have peripherals and memories that are addressable. They're the same thing that's being accessed, it's just that they're accessed at different aliases. And depending on what that alias is, it's a secure, it's a non-secure access. There's an address bit that's being used, at least on the Musca, to determine that. And then for peripherals, there's a PPC bit, I think, that's used to determine whether or not a peripheral is accessible via secure or non-secure. But when we describe these things, I mean, from a DT standpoint, the hardware is the hardware. Whether or not you're talking to a secure or the non-secure alias of the thing, it really doesn't matter. But you do have to use the correct addressing. So what we were talking about in the meeting yesterday is that we wanted to leverage the use of ranges which is one of the device tree things that in the past has been used to deal with mappings of address spaces, like PCI address space is a good example. But in our case, what we want to have happen is that you're going to have more than one way to address a peripheral, but in the end, when you decide whether or not you're secure or non-secure, it needs to be able to delve out the correct view. So that's really where I think we're going to go with this. If you look at the current pull request, and I think it's 9453, you'll see that we basically split the device tree into two separate files. One's secure and one's non-secure, and based off of a kconfig option, we include one DTSI versus another. And what that really means is that we're picking one view of the system versus another. That's not going to be how we really want this. We really, I think, want to use ranges to do this, where we have one file that has all the information in it and we don't steer it that way. But where this comes down to is that in TFM, we would really like to add the capability in TFM itself to also describe the system in a device tree standpoint, so that we can actually validate the security settings across both images, because that is one of the problems that we have is you can build one image one way, build the other image. They can completely conflict on some of these address space overlaps, and when that happens, you'll get a security fault and bad things happen. At best, you'll see an error. At worst, it just will not do anything anymore. So that's, I think, the way forward that we're going to start. I'm going to start experimenting with is the DMA, not the DMA ranges, but the ranges property, and try to pull all the DTS information back into a single file. And I think that might be the last slide. Yeah, it is. So would it be possible, I can hook up my laptop and actually show the two DTSs side by side so you can actually see what's going on. Let me do that real quick. Oh, that's a big, they're identical, aren't they? Let's see, so which do you want? It is. You guys probably don't want to see my email. Or that.
Okay, quick question just for the ARM guys. One of the things I've noticed about the address bit that does the secure non-secure, it seems like in like 90% of the cases, I don't need to actually set that bit. From the secure side, I can access things as non-secure addresses. The few cases I've found are like non-secure callable. You have to have the bit set and to distinguish whether IRQs are secure or non-secure. Is there any problem if we were to just map most things as non-secure and just use them that way? Because I mean, it has to go to the MPU, the SAU anyway to find out the permissions. So it's kind of, I mean, we don't need to have the conversation here. I'm just kind of.
So are you talking about the peripherals or
everything else?
the one thing is SAU is not really. If you're talking about the SAU configurations, they're architecturally not mandated. So if you say that I'm going to let the PPC to do the arbitration, oh sorry, in PPC I'm going to configure everything as non-secure and let SAU decide what to do, then we are kind of creating a hole where if a implementation doesn't implement SAU and it relies on the rest of the framework to do the security, then it makes a bit more complex to figure those things out.
On Musca, you can take this file on the left side and remove that bit, the secure bit, on nearly everything in there, and it doesn't behave any differently. You can put the code at 0, 2.
Because you're running by default secure, and secure can access either. That's the only reason why it would work.
Okay, so so when you talk about secure, there are two modes there, right? The secure privileged and secure non-privileged. Secure privileged, of course, has access to the whole system, including non-secure world. But when you're running services in non-privileged mode, that's where the level 2 and level 3 come in the picture. in which case your services will not have access to the, yeah, so I think now I understand your question. That will probably not work. It will work for the privileged part of the software because it can access anything it likes in the whole system. Not so much for the services. So, and in most of the cases, the ownership of the peripheral is going to be with the peripheral with the service anyway. And
I guess I'm just having a hard time understanding why this bit was put in the address, since you have to go to the cell anyway to find out progressions.
It probably comes from the, you know, A-class architecture where you've got a whole sort of more complex memory subsystem, where the bit has to travel through the memory subsystem, through the caches, and there it's very important not to have, say, the non-secure accessing via non-secure transactions and the secure side accessing via secure transactions. You can get memory aliasing problems in the cache, things like that, but which probably don't apply to these systems, but making assumptions about the memory subsystem is probably not a good thing.
Yeah, although cache is becoming a concern since they're starting to get added in. But like David was saying, I mean, you can see the secure view is on the left, the non-secure view is on the right, and you can see that the only reason why the flash is different is the offset, because it has to be offset. But basically, there's a bit, a high bit that's used to discern whether or not you're secure or non-secure, and it's a cheap way of doing it. That's really, I think, what it comes down to. But right now, we're maintaining these two files separately, and it would really be best if they were folded all into one, so that we don't have to. Because really, the system view is it doesn't matter. From a system perspective, there's an address space that backs these aliases. So, but at least now you can see what we're talking about when we talk about the fact that it's the same peripherals, but it's a different address alias. So, and as David said, you know, if you're running privileged secure, it doesn't matter which address space you're using, it'll work. But the moment that you go unprivileged, it all, you know, it's all off, because it depends then on the security settings and what the SAU is doing. So I think we're right up to the end, aren't we? Yeah. Okay. So any quick questions? Okay. Well, thank you.